Hi everyone, my name is José Pereira. I am a biochemistry PhD candidate at Universidade de Aveiro in Portugal. Today I'll be showcasing ProtoSyn, a new Julia-based tool for molecular manipulation and simulation. But before that, a little backstory. When I started my PhD, we were interested in trying out some new machine learning models for molecular energy estimation. There are tons of new tools that have popped up in the last few years, such as the Torch-Ani model, which estimates internal energy with DFT level accuracy, for example. And if all of this is just gibberish to you, don't worry. We just wanted to experiment with new machine learning models and other modern methods for energy and force calculations in molecular simulations, specifically in protein design. Existing tools such as the Rosetta software and its Python wrapper, PyRosetta, could probably get the job done. And don't get me wrong, Rosetta is amazing and has revolutionized the way we make science and protein design. However, for our purpose of integrating with more modern or experimental technologies, there were some issues. For starters, Rosetta is not open source, and it's a perfect example of the two-language problem. When we started our work, there was no support for GPU or distributed computing, for example, and finally, the documentation was infamously not up to date. So we started developing ProtoSyn. The objective was clear. We needed an open source, beginner-friendly, and well-documented platform to try out new models and algorithms in a plug-and-play environment. And Julia seemed like a perfect fit. It was not only fast with an easy syntax, it also allowed easy access to GPU computing, distributed computing, and other good-to-have technologies in the field of computational simulations. And so after almost 3 years of development, ProtoSyn now boasts a wide range of functionalities that we'll quickly try to explain by dividing into two main areas of development. On one hand, we have the molecular manipulation suite of functionalities, and on the other hand, we have some interesting methods for energy calculations. Put the two together, and we have a completely Julia-based simulation platform. On the molecular manipulation side, I could probably spend my 8-minute talk just listing all the ways ProtoSyn allows users to change molecules. Very quickly, some examples include performing mutations, conformational changes, generating structures from amino acid sequences, much more. Users can even work with ramified structures, cyclic peptides, and all sorts of weird conformations. A recent and highly requested update also includes support for non-canonical amino acids, so really, the imagination is the limit here. And the other part of ProtoSyn deals with energy calculations. This is notoriously a much harder problem. ProtoSyn intends to be a playground where modern models for energy and force calculations can be experimented with or parameterized. Even so, we plugged in some interesting tools from previous works in the scientific community, deviating a little bit from the classical usage of force fields so that new users don't have to worry about atom types or parameterizations. We try to provide the cleanest out-of-the-box experience as possible. Alright, so ProtoSyn intends to be an open source, easy to use, well-documented tool for molecular manipulation and simulation, with a focus on protein design and lowering the entry barrier for new scientists. Seems challenging enough. Next up, I would just like to show some code. It was hard to decide what sort of example would fit the format for this presentation, but I've prepared two examples. First, we'll just go over how ProtoSyn handles a sub-problem of protein design, which is the sidechain repackaging problem, and then we'll basically do the same, but introducing some mutations. First things first, we need to load a structure to be our target. In this case, we'll download it directly from the protein data bank. Some, if not most, of the structures in the PDB do not have bond records, but ProtoSyn is able to infer these from interatomic distance matrices. Under the hood, ProtoSyn uses templates for some of its manipulations. In short, it looks up that amino acid template and then copies the information to the loaded structure. So we'll just make sure that we are using the default atom names, and then we can assign charges, for example. Note that in some cases we're calling the peptides module before the function name. This is because ProtoSyn is built in a modular way. For each different type of molecule, there is a ProtoSyn module that expands the core methods by assuming certain prerequisites particular for that molecule type, in this case proteins. I feel like this follows Julia's philosophy of multiple dispatch pretty well. And so for the simulation part, in essence, ProtoSyn can be divided into three sets of functions. The main simulation functions are called drivers, as they drive the system into new conformations. These are composed by the other two parts, the mutators, which introduce a mutation either in the sequence or in the conformation, and the calculators, which evaluate the current system's energy and allow the drivers to make decisions. Perhaps the simplest driver is a Monte Carlo driver. Each step it introduces a change, evaluates that change, and decides whether to continue this chain of events or recover the previous conformations. Seems simple enough. Let's add all the required parts. We'll use ProtoSyn's default energy function for the calculator and the simple dihedral rotation for the mutator. This simply picks a dihedral angle and rotates it. Note that ProtoSyn comes with a rich selection syntax so that users can pick and target what regions or even individual atoms should suffer the conformational changes. In this case, we'll pick the chi dihedral angles of amino acid number 14, for example. Next, and optionally, we can define a callback. This is simply a function that spits out information from the ongoing simulation. We also need to define the total number of steps and a thermostat. This is a particularity of Monte Carlo drivers. It essentially dictates the likelihood of accepting less favorable conformations. We'll just use a linear temperature quench for this simulation. Alright, let's just set the initial dihedrals to something random and see if we can retrieve the natural conformation for this sidechain. As we can see, the sidechain slowly rotates towards the natural conformation. Of course, that this all hinges on the accuracy of our energy function, which is a work in progress for ProtoSyn. Now let's just quickly go back to our code and add some mutations instead and see if we can optimize its placement in our structure. Now we're doing some protein design. Of course, that for this presentation I'm sort of rushing everything, but if you're interested, you can visit the project's GitHub page and check our 15 plus examples and tutorials. Hopefully I've sparked your interest in this new package for the Julia ecosystem. We feel like this can be useful not only in direct simulation protocols as shown here, but also, for example, to generate libraries of mutation candidates or close to target conformations with just slight changes from the crystallographic structure, for example, to parameterize new energy models. In either case, ProtoSyn offers a playground for molecular manipulation and simulation. Be sure to check the project's GitHub page, and I'm happy to answer any question that you may have. I love to talk about this stuff. Cheers.